forces at D. But what about part B, the internal forces in B to C, which is this two-force member over here. So I'm going to pick up right over there. That's what we finished taking notes on. And so let's do part B here. And so for part B, we want to find these internal forces in B to C. Well, in this one, they don't specifically tell us where we need to make a cut. In the other one, they told us specifically at point D. In this straight two-force member, so I'm just going to arbitrarily say, oh, let's just make a cut right there. So I'm just cutting through B to C right there. I'm going to make a cut right there. We will have an applied force here of that force that we found in B to C. And we found FB to C was in compression, and it was 44.4 kilonewtons. So there's our 44.4 kilonewtons. That's the force in the two-force member that we had found from the FBD of the whole thing. I'll highlight it right here. It's that one right there. So we've drawn it. It's pushing on A to B. And so how did we drew it in the opposite direction when we drew this FBD over here of B and then a cut there. So this is point B, is that spot right there. Well, notice my cut, a couple of key things here. My cut is perpendicular to the length of the member, right? And my cut is perpendicular to that length. And then we can draw our normal force. We'll draw it in tension, and notice that it is along the length of the member. My shear force will be perpendicular, and I'm going to draw it so it goes clockwise rotation. And then my moment is tension on the bottom and compression on the top there. Now, if this is a two-force member, that's at an angle like this, let's go ahead and let's incline our axes, because everything is on an incline, right? Our FBC is at an incline, our normal force, our shear force, they're all on this inclined axis. So let's incline our axes. And then if we sum forces in the X direction, we're going to find that N is actually equal to a minus 44.4 kilonewtons. So it's telling us, well, there's a compressive normal force in there, and that makes sense, right? We have that member is in compression, and so we find our normal force to be negative, which means it's compressive. If we sum forces now in the Y direction, we're going to find that V is the only thing, and we're going to find that V is actually equal to 0. And if we sum moments, and we talked last time, let's always sum moments about the cut. So if we sum moments about that cut right there, then we're going to also find that the moment is equal to 0 as well. So anytime we have a straight two-force member, V is equal to 0 and M is equal to 0. We've dealt with straight two-force members before, specifically trusses. Trusses are entirely composed of straight two-force members. And so we didn't even draw the V and the M. We were making cuts through them, and V and M could exist, but we didn't even draw it. We didn't even talk about it because we hadn't gotten there yet, but because there's 0. And so anytime we have a straight two-force member, V is equal to 0 and M is equal to 0. Now on your homework problem, you have a curved member, and you're asked to find the internal forces for that curved member. So what if it's curved? What if we have a curved member here? Well, let's still take our same two-force member. So if we put B right here, and then we think about, well, what about point C being down here? We still have our FBC here equal to a 44.4. Well, what if our rigid object does something like this, where it curves like that right there? Well, if we made a cut, first we're going to make a cut here, and well, actually, let me draw it. What if we made a cut about right here? If we made a cut right there, now our normal forces is going to be perpendicular to that cut, and it's going to be some component of FBC. Our V would be parallel to that cut, and our M would be here. So curved or a non-straight two-force member. In this case, V is not going to be equal to 0, and M is not going to be equal to 0. So we can have a two-force member that does have a V and does have an M, but we usually, in trusses, we never saw that, and that's why, because we don't want the V and the M in there. But on your homework, a couple of things, right? Notice that it's always, our N and V are always perpendicular to the parallel and perpendicular to those cuts right there. Okay, any questions about that? Okay, let's go ahead and let's move on now to what we're going to do now is we actually have 2 lectures on shear and bending moment diagrams. So specifically, we're going to be looking at V and M and plotting how they change across a rigid object. Our learning objectives for shear and bending moment diagrams is to be able to make a cut at a distance X now. So we're going to symbolically say it's a distance X, determine the V and M in terms of the distance X, the known loads, including distributed loads, concentrated forces, and couple moments. Need to be able to define the bounds on which the equation are valid. And then also we'll talk about the mathematical relationships between W, V, and M. They give us, we see these really cool relationships, and we'll talk about how we can use those more after spring break here. So just a reminder about our upcoming calendar. Remember, no homework due on the last Sunday of spring break. We do have handwritten homework number 9 is due today. And then we'll pick up we'll pick up on Monday with another lecture on shear and bending moment diagrams. The first homework problem on VMN is really an introduction to drawing those diagrams. They just walk you through like how to add lines and how to make the plots. And so you don't have to include that with your handwritten homework. And then our first real homework problem then is a simple supported beam with a concentrated force right here at the specific distance. So we're going to plot what does the V and M look like across the whole length of that member right there. Number 2, we see a similar simply supported beam now with the distributed load over part of it. We see a fixed support in this one, so a cantilever beam with a concentrated moment with a distributed load on there. And then actually our second homework on V&M, because we have 2 lectures, we'll have 2 homeworks on the V&M diagrams. This is a really important topic for the next class, solid mechanics or mechanics of materials. Also very applicable and relevant, like we talked about last time, where every single structural member, to figure out how big it needs to be, we need to be able to do the V and the M. And more specifically, they do a V and M diagram that engineers do when they're designing buildings and bridges and anything that has a load on there, and they need to size some sort of structural element, even like a car frame or something like that. So we have this one with a concentrated moment there, another one with a fixed support, and then this one, the last one that you're going to see, has got all this stuff going on. It's got a cantilever section hanging out over here. It's got concentrated forces, concentrated moments, etc. Now, to give you an idea of where we're going and what we're trying to get to here, this is a document that's up on Canvas, and it's actually part of the hands-on number 6. Hands-on number 6 can be done completely remote. You don't have to do it during recitation. You can do it on your flight home if you want to. Yeah, I mean, you have to have online, you have to be able to get on Canvas, but this document is up there, and it goes through, like, I think 11 or 12 different key cases for V and M diagrams. And so this is for a simply supported beam with a distributed load. I'm showing here a deflected shape. So what the deflected shape looks like, there's our smiley face, which means there's tension on the bottom of that whole thing. And then the next thing I show is the free body diagram to find our support reactions. The V diagram actually looks like this, where it starts up here at AY, and then it's linear and it actually crosses through 0 and then ends at negative BY, the support reaction there. Our moment diagram for this problem looks like this. It actually, M starts at 0. And the reason that it starts at 0 is because the left end face does not have anything preventing it from rotating in. So there's nothing preventing that rotation. So it rotates in, our M right there is 0, and then it reaches a maximum value where V is equal to 0. That is always going to be the case. And then it ends over here at M0 because the right end face can rotate in. There's nothing preventing it from rotating in. So this is what we're really going for, is to be able to do all this stuff. But so I wanted to show you where we're headed here. This the quiz here goes through a bunch of cases. How about with just a partial distributed load? So all this is up on Canvas for you all. It's part of hands-on number 6. We talk about some of the really key things here. So use this when you're working on the homework, as well as when you're doing the doing the hands-on number 6 as well. Okay, so let's jump in over here and let's figure out how are we going to end up, how can we do this for, how can we come up with those diagrams? So we have V and M diagrams. And essentially what we're doing is we are making cuts at a distance X. This is basically what we're doing. We're going to draw the FBDs. From those FBDs, we can figure out these V diagrams, and we can figure out these M diagrams. The reason there's no N diagrams, like November for November N, is because the normal force usually doesn't vary across the length of the member. It's usually constant. So it's really not a whole lot of a point of doing a diagram or a plot of that. So let's take a look here. We're just going to jump right in to an example problem. And so for this example problem, we are given that first one actually that I just showed you on those key cases document that's part of that hands-on number 6. We're going to take a simply supported beam and we're going to apply a uniform distributed load of 100 pounds per foot. We have this right here is a pin support at point A. Over here at B, that's a roller support there. And we're going to look at a total distance across here of 10 feet. And what we want to find for this problem is we want to come up with our V as a function of X. And I'm going to use square brackets so we don't confuse that with like V times X or something like that, M of X. So we want V of X, M of X, and the diagrams as well. So we're going to come up with the equations for those and also the diagrams all in there too. So let me add some more arrows to our distributed load here so it looks a little bit more like our typical distributed loads look. And so, oops, that's not our solution, right? That's what we're asking to find here. So let me change that. This is what we're asked to find. We're not quite to the, so let me change that from solution right there. I'll highlight it from solution. I had written solution there. I was getting ahead of myself. Okay, but yes, let's do now. We can do our solution. Okay, well, the first thing that we need, just like last time, if we're going to make a cut anywhere in between A and B, well, we're going to go to the left of the cut or we're going to go to the right of the cut, and we need to find our support reactions, don't we? we need to find AY and we need to find BY. We need to find those first. So our first thing that we're going to do is an FBD to find the support reactions. And so that would be, in this case, that's going to be an FBD of AB, right? And so let's see, we've got point A, we'll put right here. How about we put point B right there? At A, we're going to have an AY, which is, if we can solve it actually here in a second. Let's get the whole FBD up here. AX, over here, we'll have a BY, and then right here, we'll have our distributed load that's acting over that whole thing, and W is 100 pounds per foot. And we know that's acting over this distance here of 10 feet. So can anybody tell me just by observation, what is AY going to be equal to? Anybody in my front row here? I know I saw some people. Oh, I think I saw Zoe. Zoe, what's AY? Can you figure it out without actually summing moments or summing forces? Yeah, Brent said 500 pounds. Maybe Zoe's like on an airplane right now. She's probably flying home, right? Watching statics. Anybody doing that? I was kind of curious. Anybody like sitting on on the airplane, like watching statics lecture? That'd be kind of cool, right? Like the person next to you be like, what the heck are you doing? Okay, so yeah, 500. So Brett, yeah, that's right. Yeah, 500 pounds because the total is 1,000. The FR would be right in the middle. And so AY and BY are both going to be 500 pounds. So yeah, that's our first, right? We got to have AY and we got to have BY. Now what we're going to do is we're going to come in here and we're going to make a cut. And we're going to cut through everything. We're going to cut through our distributed load, but we're going to make that cut at a distance X. And we always measure X equals 0 is always going to be at the left end of that beam there. So let's write it down separately here. X equals 0, always at the far left point on our rigid object. So X equals 0, always at that far left point. And then we're always going to measure X, then getting bigger to the right. And so there's our cut that we're going to make. And actually, just like before, we can go to, and no problem, Zoe, about your mic not working. It's not a big deal at all. And so we can go either way. We can go to the left of the cut. We can go to the right of the cut. And actually, we'll end up doing both. In this first one, though, let's go to the left of the cut. And so our second thing here is going to be an FBD to the left of this cut at our distance X. So last time we did this at a certain point. We made a cut at point D, and that was exactly at 4 meters. Well, today we're going to make the cut in terms of X. So there's our cut right there. And we cut through when we're doing our FBDs, we cut through everything, including any loads. So we have our distributed load up here. We know that's 100 pounds per foot. And we have in our FBD X feet of that 100 pounds per foot. We also have, we had already found this, that AY was equal to our 500 pounds right there. I guess we didn't talk about AX, but that's the only force in the X direction. So AX would be equal to 0. So we made this cut, and so we're going to have our internal forces there. Well, we will have an N. We're not worried about N, but it can exist on there. And then we will have our V, and we're going to draw all these in terms of our positive sign convention. So V is going to go down. V is going to be a function of x. So I'm using square brackets to denote when we have a function. So this is v as a function of x. And then our m is going to be positive. So it's going to go, when we're looking to a section to the left of a cut, it's going to go counterclockwise. And that's our m as a function of x. I also want to draw on here. Let's draw our FR for this FBD. FR would be right here. And so we'll figure out what FR is equal to, and also where, and actually I didn't quite get it where I wanted it to, because shouldn't it be right in the middle of that from left to right of X right there? So there's our FR, and that distance there is going to be equal to what right there? So if FR is right in the middle of our distributed load for this FBD, what is that distance right here from the cut to FR? Anyone? Yeah, half X, right? Yeah. So it's going to be exactly 1/2 times X is that distance to FR from the cut right there. Okay, and then what is FR? Well, FR is just going to be equal to a, it's the area of our distributed load. So how about somebody else that hasn't chimed in yet? Prash or Sean or whoever, Mackenzie, whoever turns on their mic first. Or Kalev got it. Okay, so whoever chatted first. So FR is going to be 100, because that's the height of the rectangle, and then X is the horizontal distance. So it's just FR is just equal to 100X. So we were doing everything exactly the same that we have done before with this. It's just now the cut is at a distance X instead of being at a specific spot. Well, now we can do things like, well, let's sum forces in the Y. And I've got my positive sign convention for equilibrium is going up. Remember, V of X going down was positive for internal forces. We have two sign conventions that are going on. So when I get to my equilibrium sign convention, I look at my V of X and say, oh, well, that's going down. So I'm going to say that's a minus V of X for equilibrium, even though it was really a positive V for our internal force sign convention. So I have a minus V of X, and then plus a Y, which is 500 pounds, and then a minus FR, which is 100X. And that has to be equal to 0. So we're going to find, when we solve for this, that V of X is equal to 500 minus 100X. We can use this equation to figure out what is V at X equals 0. Well, we just plug in X equals 0. It's equal to AY, isn't it? When X is equal to 0, our V is equal to AY. And we can also think about, remember I showed you that picture before where B actually crossed through 0. We could figure out where B does cross through 0. Couldn't we use this? Couldn't we use this to figure out where is V equal to 0? And we'll talk, right? We just set this equation equal to 0 and solve for X. We'll talk about that a little bit later. Let's find M of X. Let's sum moments about the cut equal to 0. We have our, again, an equilibrium sign convention. We also have our internal force sign convention. This one is going to be M of X is going to be going in the positive direction. So the moment at the cut right there. FR is also positive, so plus a 100X times X over 2. And then AY is going to be negative, so minus a 500 times that whole distance of X right there. And so we're going to find that all that has to be equal to 0. We're going to find that M of X is equal to a 500X minus 100X squared over 2, or 50X squared. That's funny, Basil. I like that. It's a convention to use square brackets for variables and rigid objects, right? Yeah, because the square brackets, like, they're rigid, right? They're not like curved and smooth and flexible. Okay, so we came up with our v of x equation. We came up with our m of x equation. We could absolutely now plot those, right? We could plug it in our calculator. We could think about what those equations look like, and we could plot those. But before we do that, I actually want to ask anybody if they notice any relationships between the v of x function and the m of x function. Any mathematical relationships between those two functions? Linear parabolic. Okay, so that's looking right. Yeah, so we have just the expression, but how about like from v of x to m of x, or from m of x? Yeah, there. Okay, I see it in there. Yeah, vx is the derivative, right? So if we took the derivative of m of x, we would get to v of x. Or if we took the integral of v of x, we would get to m of x. And so actually, that's kind of crazy when you think about it, because how did we come up with these? We came up with them by summing forces on an FBD and summing moments on an FBD. Well, that relationship is always going to exist between W, the distributed load, V, and M. So let's look at our mathematical, and write this down, relationships for V and M. Okay, so, and let's actually start from the FBD. So from the FBD to V, the slope of V is equal to W. Or mathematically, we could say that was dV dx is equal to W. Do you see that in our equation? What's the slope of V? It's minus 100x. What's W? It's 100, and it's going down, and so it's going in the negative direction. So that's why it's minus 100. The other one that we have is the change in V is equal to the area under W. This one we could say mathematically that delta V is equal to the integral of W dx. That one's not so obvious right now, but if we did integrate W, that would be how much V is changing over whatever range we are looking at here. Okay, and then the other one that's not going to show up in this one right just yet, but we will see it later, is that a concentrated force, causes a jump in the V diagram. And actually, we can kind of see it here. AY is a concentrated force. It's 500 going up. Well, where does V start? What's the V at A? At x equal to 0, V is equal to 500, isn't it? And that's because there's that concentrated force. So we can kind of think about if V started at 0, before we got to A, and then we reach this point A right here, and there's a concentrated 500 pounds going up, then that means it's going to jump. The V diagram is going to jump up, and we'll plot the V diagram here in a little bit. The next thing let's look at is from V to M. So these mathematical relationships now from V to M are going to be very similar to these ones that we just wrote down. The first one, let's talk about the slope. The slope of m is equal to v, or dm dx is equal to v, right? Isn't that's true if we look at our two highlighted equations? What's the slope of the moment diagram? The slope of the moment diagram, right? If we took, how do we get a slope? We take the derivative. If we take the derivative, what do we end up? We end up with v. So the slope of m is equal to v. The next one is the change in m. Change in m is equal to the area under v. Or we could say this as delta m is equal to the integral of v dx. We're going to use these very practically. We're going to basically look at the FBD and figure out what the slope of v is equal to based on the value of our distributed load. Then we can look at v and figure out what m looks like based on the value of the shear diagram. And then our last one here we have for v to m is that a concentrated moment, when we don't see that in this at all, a concentrated m causes a jump in the M diagram. Okay, so we have our mathematical relationships. Let's draw, and the way we're always going to draw V and M diagrams is directly below the FBD, because we see from these relationships we go from FBD to V, and then we go from V to M, and so we can stack our work this way. So leave some spot on your paper to draw. Let me show you what we're going to do here. We'll put our FBD here. And then right below that, I'm going to do a dashed line right here. Right below that, how about like right here, we'll put our V diagram. And this is going to be in units of pounds. And then right below that, we'll put our M diagram. And this is going to be in units of foot pounds. And so then we'll make X going off to the right here, increasing. So there's our X, and then right here, we'll make X go off to the right there. And so let me add, stack that on your paper. And then let me add our AY right here, right? We know AY is 500 pounds. We have our distributed load that's acting over that at 100 pounds per foot. That's our W. And then we know that this is our L of our length there is 10 feet. And so we're also going to want to know where the beam ends, because we want everything relative to each other. And if you think about this, if we were doing this for design, we want to know where all this stuff is happening. And we want to know, okay, well, where is V maximum and relative to our actual beam? What exact spot on our beam is V maximum? What exact spot on our beam is M maximum? Well, if we took our equations, we could certainly plot these. But let's use those mathematical relationships. So our first mathematical relationship is the slope of V is equal to W. Well, actually, even before that, though, we got to figure out where V starts. Our V starts, well, we can think about our concentrated force, our AY of 500 pounds right here. And so if AY is 500 pounds, it's going up. We can think about that as causing a jump in the V diagram from 0. And so we're going to have V is equal to AY right there at that spot. So that's where we start. We figured out where we started. Again, we could plug in our equations. It's 500 minus 100x. At x equal to 0, we know that it's going to be AY, which is 500. And then now we can use our slope of V is equal to W. What's W? It's 100 pounds. And so it's going to go across linearly like that. So our slope is equal to minus 100 pounds per foot. My spot right here for this one, that we are going to have a V equal to 0 right there. So we have a V is going to be equal to 0. Now we do need to figure out where is that going to be? Where, at what distance is V equal to 0? Because if we think about it for the moment diagram, isn't that if the slope of the moment is equal to the value of the shear, then wouldn't that mean when shear is 0, that our moment diagram has a slope of 0, meaning that that's a maximum or a minimum? Okay, so that point is going to be really key. We'll talk about that here in a second. Over here at B, I forgot to write BY in. We do have a BY equal to 500 pounds. Notice that our V right here is equal to a minus BY. That's always going to happen. It's just based on our positive sign convention for V, that we go from a positive V equal to positive AY to a V is equal to a minus BY. It actually changes direction of the, it changes from on the left side of the beam, it's in a positive shear. On the right side of the beam, it's in a negative shear. Okay, let's go ahead. Let's figure out where does V equal to 0. We know it's going to be equal to 0. All we have to do for that is take our V of x equation, which we found was 500 minus 100x, and we can just set that to 0. So where is 500 minus 100x equal to 0? It's at x is equal to 5 feet. So we know that this distance over here in green, that's equal to 5 feet. Okay, how about our moment diagram? We need to figure out, again, where it starts. Where does the moment diagram start? And then once we know where it starts, we can then use our mathematical relationships, knowing the slope of m is equal to v, to figure out where it goes from there. This is simply supported. So when it bends down like this, the ends bend in. And so there's nothing restricting rotation right there at that pin. So from that, we can tell that our m is going to start right here at 0. So m is equal to 0, and that's because it's a pin support. Now, again, we can use our equation, can use that equation that's 500x squared minus 100 or 500x minus 100x squared over 2, right? We could certainly use that equation to figure this out, but I want to use our mathematical relationships. So what is the slope? Where do we start with our slope? Our slope is equal to the value of our shear. Our shear is positive. So that means our slope is going to start positive. And then what happens to our shear? Our shear gets smaller and smaller and smaller and smaller until we get to V is equal to 0. So doesn't that mean it's going to look like that? Right here, our slope is equal to 0. And we have our m is max. So our slope here, right at the very beginning, is equal to AY, right? Because that's our value of our V right at the beginning. It's equal to AY. So we have this really big slope. And now what happens to our V? Our V becomes negative. So it becomes a little negative, like it's a small negative value, then it's a bigger negative value, and then it all comes all the way down here to a negative BY. So then the rest of this, then we go, it starts to get negative, 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 and we are going to end at 0 right here. M is equal to 0 at a roller as well. If you plug this in the equation that we derived, if you plugged in x is equal to 10, you would find m is equal to 0. Okay. What about now? What is m max? We could plug in, we know exactly where it occurs, right? It occurs at x is equal to 5. So we could plug it into our equation. Or let's use the fact that delta M is equal to the area under the shear. Could we find the area of this triangle up here? A1 would be equal to 1/2 times 500 times 5. So that's going to be equal to 1,250 foot-pounds. Now this is the change, that 1,250 foot-pounds is the change in M from x equal to 0 to 5 feet, because, or let's say 2x is equal to 5. From x is equal to 0 to x equal to 5. Because that's A1 is from 0 to 5, isn't it? So that's the change in M. How about the change in M from the delta M from x equal to 5 to x equal to 10 is going to be, delta M is going to be a minus because it's negative, it's below the v-axis. It would be A2. So this one over here. Call that A2. And just let me highlight A2 so it's easier to find. There's A2. And isn't A2, it's going to be equal to A2. A2 is a minus 1/2. The base of the triangle is 5 feet. The height of the triangle is 500 pounds. And so it's a minus 1,250. So that gets us back to 0, doesn't it? Because that's the change in M from 5 to 10. So our change in M from 0 to 5 was positive 1,250. But then from 5 to 10, it's a minus 1,250. So that gets us back to 0. So we really did 2 ways we can come up with these diagrams, didn't we? We did the equations, and some of the problems on the homework, they're going to ask you for the equation. Some of the problems on the exam, we're going to ask you for the equation. Some of the problems on the exam or on the homework, we're going to ask you for both or for just the diagrams. And so knowing both these methods is really important. Now, let me go back to the diagram, the key cases thing I was showing you. Now I bet this makes a little bit more sense. And I explain a lot of this that's going on. Like b starts at ay because b is equal to ay when x is equal to 0, which is right here. We see this v equal to 0 right there. We see an m max. And I talk a lot more in detail about why we see all this stuff. So now, do you think we could do, actually next time we're going to do a problem like this. I want to point out, I know I'm basically out of time here, but let me point out a couple things. Our slope is 0 in the first part of v. V is still equal to ay right here, but our slope is 0 because w is 0. So it's just constant. And then we see a shift, a change in p because we have a concentrated p. And then it goes down to v is equal to minus by. Again, our slope is 0. And then how about our moment diagram? Our moment diagram still starts and ends at 0, but because now we have a constant shear, our moment is now just linear. Okay, we'll do examples like this. We'll do all our cuts and find all the equations and do all that stuff next time.